Hi, I'm Josh Calapos, and my computational photography project was implementing the paper Scene Completion with a Million Photographs. Scene completion is useful when we have an image with missing or unwanted regions. Our goal is to fill in these gaps with new image data such that the new image appears unedited. While other methods attempt to fill in this missing region with information from the same image, we find semantically similar images and use them to create a realistic output. As you can see with this example from the paper, the roof of this building is in the way, so we mask it out and find multiple scene matches that we can use to fill in the gaps. In the paper, when given an image to complete, the authors used a database of millions of photographs to draw up a set of semantically similar images. Their note is that, though the space of all possible images is effectively infinite, the space of semantically similar scenes is surprisingly small. I actually don't implement this part of the paper, but it's where the million photographs comes from in the paper's title, and I do use some of the matches that they find using this strategy for my scenes. The portion that I do for my project is described in the paper as local context matching. After finding the right image to fill in with, there are three main steps that follow. First is image alignment. Although the paper notes that similar images are usually pretty well aligned from the start, it is worthwhile to do a local search of different translations and scalings to find a better match between the two images. Once this is found, we use a max flow algorithm to find a minimum cut along the image. This starts along the original mask, but we want to promote blending between areas that have lower frequency changes along our seam boundary. Following finding this cut boundary, we follow it up with simple Poisson blending to give a boundary a hopefully more believable smooth transition. This gives our completed final product. Now here are some results of my project. On the top left is our original image with the night sky that we really like, and we want to get rid of the dark town on the bottom. We indicate what we want to keep with a simple mask that you can see here in the middle. For our matching scenes, we have an arguably equally beautiful sky, but we're going to just be taking the nice sunset. Our final product is a nice blend on the right. These two night skies look pretty similar, so they blend together pretty nicely. Here we try to replicate a result that the paper produced, but now with my implementation. Just like before, we are removing the roof that is in the way and replacing it with a more clear view of the ocean with boats. The blend along the water is almost imperceptible, almost as if the boats were always there. Here's another example where we've replaced the wall on the right with a new wall from a different image. The new person that we picked up, fortunately, is situated in a way where his size may be realistic, but we're approaching some flaws in this technique that we will discuss soon. This image also came out pretty well. Here we have a town, and we want to replace the hills in the background with something different, so I put the town by a lake and some mountains. Though a lot of images come out great, there are some unavoidable issues with this technique. One is that we may get incomplete objects because we are cutting along boundaries given to us by running the max flow algorithm, and this algorithm does not have any idea of what a complete object may be. In another rendition of the street scene, we have created floating ghost cars, or at the very least a portion of a ghost car. They've been cut along the ridge of the car door, which is unsurprising. Ideally, though, we'd have liked to have the whole car, even if it makes the scene a bit more cramped than before. The same goes for scale. While we have a sense that people should be about the same size, and ducks should not be as large as a pond, scene completion does not have that concept built in anywhere, and thus does create some interesting scaling mistakes. Not really considering a semantic meaning for scale has allowed us to create this human sea monster. While maybe a cool movie idea, it's not difficult for any viewer to say that this image is not real. A third issue would be that sometimes, the perspective of a completed image is slightly off, which is easily detected by our eyes. Despite these problems, trial and error with different semantically matched images will often produce a pretty convincing output. Overall, scene completion with a million photographs has proven to be effective at giving the impression of a natural, untouched photo. Although I didn't run my own quantitative evaluation by asking people whether they thought my photos were real, the authors of the paper did, and they were able to fool the viewer around 37% of the time. This was great compared to an earlier technique that only fooled people 10% of the time. This class and this project has been an enjoyable experience for me, from which I have learned a great deal. I hope you have enjoyed my presentation, and thanks for listening.